Good morning. Today we have one more problem we want to discuss for method of images. And after that, we're gonna talk about separation of variables. Separation of variables will be a longer topic. We'll roughly spend 3 lectures on that. It's about more general ways of solving Poisson and Laplace equations. But first of all, let's look at this particular problem, method of images. We have a point charge Q and it's at a distance z away from a center of a conducting sphere. Now this conducting sphere is grounded, so it has potential 0. It has a radius r. Now the question is find the potential everywhere. Okay, so and it's a method of image problem. You know that you can solve this by putting an image charge somewhere as equivalent. So you change this problem into equivalent problem of the real charge and the image charge. So I'm going to give you guys some time to discuss where do you think this image charge needs to be located. So spend a couple minutes in your group to talk about where do you think this image charge needs to be. Okay, and then you can take a screenshot before you discuss. Okay, so everybody came back now. The question asked, where is the potential? What is the potential? Find the potential everywhere. Now, looking at all space, there are two obvious regions. The region that is r less than r and little r is bigger than r, right? Inside the sphere or outside the sphere. That pretty much covers what we mean by everywhere in space, right? Everywhere. So if there are distinctions of those two different regions, and you need to put a image charge somewhere. So where do you think we should put this image charge? Here or here? What do you think? Inside the conductor at r less than r, or outside at r larger than r?
So is it supposed to be in this? Because I thought we would have to put this image charge at a distance minus c away from your sphere. I'm guessing that's not correct.
At a distance where? From where?
Minus c.
Minus c would be outside then, right? Yeah.
Okay, then yeah, I think it's outside.
So let's think about what happens if we put a charge outside. And let's think about what is the condition for real method of image to be useful. First of all, you cannot change whatever the Poisson equation is. Now, as rho simply mean that in the region you're interested in, you have some kind of charge density. Here, in region we're interested in, for example, if we're interested in here, there's no charge except this Q, right? So you cannot change the charge density. Thank you, Justin and Benjamin, for putting in the chat. But if you put a real image charge anywhere outside, wherever you put it, the outside space is no longer the same charge distribution. You have changed the density rho. You have already, it's not, how you mean, what do you mean by change? It's not Q anymore, there's something more. So you can see no matter where you put this Q prime, you cannot put it outside. Outside, you cannot change the Poisson equation, right? All right, so the only way is to actually put it inside. Now, where do we put it? So, and a good intuition could be, well, if we are treating this, I'm drawing my intuition from where we have a flat mirror, sort of quotation mark mirror. If we treat this as a spherical mirror and an image, where is an image? So I think, well, if it's here, then I'm gonna say my image is probably somewhere here. It doesn't have to be, I'm just saying, what if it is there? And I'm guessing it has a distance z prime from the origin and has, it needs to be a charge that's q prime with the total amount of charge q prime. And I'm going to solve what z has to be, and I'm going to solve what is q has to be, q prime has to be. So that tells me what kind of charge and where would I put it if I can solve these two quantities, z prime and q prime. Okay, all right, so I know that by putting an image charge, I need to have the same boundary conditions, right? By looking at, so that means everywhere here, we should have potential 0. Everywhere here on the sphere, we should have potential 0. So I'm saying, okay, I'm gonna pick 2 points from the sphere. 1 point is here, and 1 point is here. I know that if the q prime is putting in here, it has to make potential here to be 0, potential here to be 0. It needs to satisfy the same boundary conditions. Okay, so let's see what that would give us. So I'm looking at this point. Let's call it potential at point P. So the potential at point P is due to charge Q and charge Q prime, right? Those two charges. And charge Q is KQ over the distance from P to Q. And look at the diagram, it's going to be Z minus R, right? Z minus R. And look at Q prime, it's going to be KQ prime over the distance from Q prime to P, and that is going to be R minus Z prime. Okay, radius minus Z prime. So I have that. And I know that needs to be 0. Okay, so that gives me a condition of Q prime in terms of Q. That tells me Q prime has to be negative Q over Z minus R times R minus Z prime. So that's first condition. And you can see we have two variables, 1, 2. So I need at least 2 equations to solve it, right? Right now I have 1 equation. But that's okay, I got another point, right? I'm gonna call this point Q. Potential at point Q has to be 0 as well. And that is also the superposition of these 2 charges at point Q. So let's put it in KQ over the distance from Q to little q, right? Point Q to this charge is 2r, is 1r plus the total distance z. So it's going to be z plus r plus KQ prime over distance from this point Q to my Q prime is big R plus Z prime. So Z prime plus R. Now that has to be 0 as well. Okay, so I got another equation that Q prime is negative Q over Z plus R plus Z prime. So that's the second equation. Now we're dealing with the same Q prime, right? So 1 is equal to 2. They're the same equation. It's all Q prime. So I know that negative Q R minus Z prime, Z minus R is negative Q R plus Z prime, Z plus R. Okay, you can simply just try to solve this. After some algebra, you found Z prime. So Z prime is R squared over Z. Okay, I found the distance. This is the distance from the origin to my image charge. Now you found Z prime, you can find your Q prime. Q prime is going to be, you plug it in either 1 or 2. So you got negative Q R over Z. It turned out we need a negative charge. Okay, we need a negative charge. And it's not exactly negative Q, which makes sense because now it's not a flat mirror. So it's negative Q times R over Z. And the distance is also given by this equation. So we are able to find exactly where to put the charge. And we find how much charge should you put there. It's negative charge. After doing that, you are able to find the potential everywhere, right? Because the potential everywhere is, take a random point here. You simply need to put in the script art from here to here and the script art from here to here. So let's say V at random location can be calculated now. So at a random location, if you're curious to find your potential at a distance at a location R away, and this is theta, for example. So what is a potential at that random location? That potential is going to be V at that location is going to be V due to Q plus V due to Q prime. And this is KQ over script R Q plus KQ prime over script R Q prime. Now Q prime you already know, we can plug that in later. And the script R Q is this distance, right? Using the laws of cosines, R is going to be R squared plus Z squared. So this is R and this is Z, and they make an angle of cosine. So it's going to be this Q prime is going to be r squared plus z prime squared or z prime cosine theta. You can plug in the z prime, you can plug in the q prime and plug everything into this equation. And you have solved for your potential at a random location, any location outside. So this method of images give us potential everywhere outside. Do we need to find a way to solve for inside, or do we already know what the answer is going to be? We know what the potential will be for inside. If you have a conductor grounded, put a charge outside, what's the potential here? Yeah, it's going to be 0, right? Everywhere here it's grounded, so, and it has no charge inside, it's hollow. So this is equipotential everywhere. Within, also on the surface, so it's going to be 0. We don't even need to calculate the potential inside. So we just found the outside. Okay, so this is one more example of how a method of images could be useful. Okay. All right, so you can see there are really only a handful of situations we can solve for method of images. We want to be able to find more universal and more general, solve for more general situations. That's why we're going to this third topic called separation of variables. The separation of variables is the idea that if your solution to your Laplace equation is a function of x times a function of y times a function of z, is a product of those functions, then we will be able to separate these variables into their own differential equations to solve it. Because then someone might ask, well, okay, let's say you want to solve for a general solution for Laplace equation. And you propose the solution is a general solution, which is some function of x times some other function of y times some other function of z. But how do you know it is in this format, right? Someone might ask. I would say, well, I don't know if it is, but I'm going to assume it is, and to see if I can find such a solution to satisfy Laplace, to satisfy also the boundary conditions. So if I succeed, then I conclude this must be the only physical solution by uniqueness theorem. So this is what we're going to do. Sometimes even if it is not exactly this format, it could be a combination of that format. For example, even if it's not a function of x times a function of y times a function of z, it could be a combination of this plus another function of x times a function of y times some other function of z. And that could be a solution. So this can actually be pretty universal and help us solve quite a lot of problems. All right, so let's get started. We are going to work with the Cartesian coordinates at first. Eventually, we're going to work on spherical coordinates as well. So to work on Cartesian, we know that v as a function of possibly x and y and z is in the function in the format of some function of x. So I'm going to say this is a function of x, big X, times some function of y times some function of z. So I assume I have this general format, and I want to see where would that get. So this has to satisfy the Laplace equation. So you can plug that in. To do this, it's really d second derivative dv dx plus dv dy plus second derivative of dv dz equals 0. Okay, so what does each of them look like? So let's work on them one by one. The second derivative of this is going to be, you can see that these two are simply viewed as a constant when you're taking derivative with respect to x, because y and z does not depend on x, right? So this is, you can treat them as a constant. It's just like you're really just taking a derivative with respect to x, and you carry the constant with you. Okay, that's the first term. Likewise, the second term is second derivative with respect to y, and x and z carries, right, as constants. The third is the same. X and y carries. So you can see when we put them back together, we got, this is the second derivative with respect to x, right? So x, the function of x, second derivative y and z plus x, second derivative y and z, last one, x, y, and second derivative z. Okay, all right. So far so good at this point?
Yep, looks good.
All right, so at this point, I'm going to divide both sides with the function itself. So with x, y, and z. Okay, so what would I achieve by doing that? The first term, when you divide it by x and y, z, what do you get? Y and z, this cancels, right? So you get double second derivative over the function itself. The second one, you get the second derivative of y over itself. The third, you get the second derivative of z over itself equals 0. Okay. All right, so I've got something that looks like this. Okay, so I got plus this plus this equals 0. So you can see this is a function of x. This is a function of y. This is a function of z. Okay, so at this point, you might wonder, well, I don't see that how you simplified our solution. It still looks very complicated. So let's look at a question that you can discuss. So suppose what we have achieved is we have 3 functions, then they add up to be 0. One of them is a function of x, one of them is a function of y, and one of them is a function of z. That's what we just got, right? This only depend on x, this only depend on y, this only depend on z. So what can we conclude about these functions? So I will let you go ahead and discuss this for a couple minutes, and then we can talk about it.
Professor, I think your screen is frozen.
Oh, yes, I'm sorry. Second, please. Thank you. So we have 3 functions. Each of them is a function of x or function of y or z, and they add up to be 0. This is mimicking the this one we just got, right? A function of x plus a function of y plus a function of z is 0. So what can you conclude about each of these functions? So you can have a couple minutes to discuss, and we will talk about it.
Dr. Ryan, do you mind scrolling up again when everyone's gone?
Yep.
So I don't think I wrote down your notes correctly. What is, let's say, for example, divide both sides by a function of x, a function of y, and is that a function of z?
Yes.
Okay.
Yeah, I know my x and z are not all that different.
I'm so sorry, Dr. Ryan. I still haven't copied down the last of your notes. Do you mind if I take a quick screenshot? Okay, just a little bit further down. There we go. Okay, thank you.
Okay, 5 more seconds. If you haven't voted already, please put in your vote. All right, I'm gonna go ahead and close this, and then let's take a look. This is our results. Okay. So would anybody would like to give a reason or a reasoning or argument for whichever choice they support?
I'm thinking it would be D because if you take the second derivatives of all those functions, you're going to get 0. And the numerator wouldn't have, or the denominator wouldn't have an effect since our second derivatives are in the numerator. This is I'm assuming that all of these functions are related to the general equation we just derived above, right?
This is just a general sort of, well, we can look at this if we were just math majors. So if we were
Okay.
just, doing this generally, what would you think?
I thought it was A because they could all be constants that happen to add up to 0, or they could be 0. Either way, it's constant. Like they would be constants.
Okay. All right. So this, if we were to mimicking what happened earlier, we were not saying we're not saying this becomes f of x. We're saying this entire thing, whatever format it might be in, is f of x. It's a sum function of x. So I don't know if that might be one of the misunderstanding, but this entire thing is depending on x, meaning that whenever you change x, it's going to change, right? No matter what this format exactly looks like. But if that were the case, if this function depends on x, I can keep y and z fixed, and I can change the value of x, and this value would change, which means they are no longer going to be 0. I can do the same thing to y. I can keep x and z fixed, and I can vary my y, and this value will change, and they will not be 0 anymore, right? So only way for this to be 0 is they each individually could be add up to be a constant to be 0. So each of them has to be constant. They cannot depend actually on x or y or z, which means that f of x has to be some constant, g of y has to be another constant, and h of z could be another constant. These, they could all be 0, but they could also be just constants add up to 0. So A is correct. Thank you for sharing the thoughts. So going back to this equation we have, we realize, oh, if they were indeed to satisfy Laplace equation like this, each of them has to be constant. So what we have done is we switched a complicated differential equation to 3 differential equations that are simpler to solve. So this is a constant. This is a constant.
Dr. Ryan, why couldn't it be linear? Because if we're saying that use a function of x to x, then
no, the thing is, I'm not saying this is linear. Is this entire, you're saying this entire thing is linear?
okay, got it. Okay, thank you.
Right? Okay, all right. So, and this, you could argue this might be linear, in which case this will be 0, and that's a constant, right? That is a one situation of what we argue is a constant. Okay, so this has to be, sorry, C1 plus C2 plus C3 is 0. Right, we have found, we have sort of treated a complicated solution with more equations to solve. Instead of one, we have three, right? 1, 2, 3, but each of them are easier to solve. So this is a trade-off. Now, let's find the solution for these cases. And I know that they're all the same format, which means I only need to solve one, right? I don't need to do X and Y, Z 3 times. I only need to do it one time. Okay, so let's solve these equations. So the first one is C1x, right? This is the first equation I need to solve. Now, the general solution to that is now, if C1 is larger than 0, I have this general solution that x, the function of x is a e square root of C1x plus b e negative C1x. You could always plug this back in to verify. You can always plug it in to verify it is indeed a solution. So that's a general format of what this look like if C1 is larger than 0. Now, if C1 is less than 0, we can get a combination of sines and cosines. Now, if you follow this particular format, then when C1 is negative, you get an imaginary number. So you have a complex exponential, e to the I of something. But e to the I can be written in using cosines and I sines. So they can be rearranged using just cosines and sines. So the general solution would be a, some other constants. So I'm going to say a prime sine of negative C1 x plus b prime cosine of negative C1 x. Now, C1 is less than 0, so I need the negative C1 to make this a positive number. Again, you can plug it in to verify. Plug it back in here to see this is if this is indeed true. Now, if C1 is equal to 0, this is like what you said, Sebastian. This becomes a linear function of x. Okay, all right. So we have, no matter what the constant is one of these 3 conditions, and we are able to find a solution to each of these conditions. So, and we just need to solve 3 differential equations. Okay, now this is as much as we will go. Now we need a concrete problem to see if this method works. Let's look at a concrete example. So I'm going to show you conductor. Looks like this. Okay, so this is example we're trying to solve. We have a metallic gutter that extends in the z direction. Find the potential inside this pipe. So this is sort of a front view. I'm gonna draw a sort of a perspective view. Maybe that will be a little bit easier, or I can add a little bit lines here to show us. So this is grounded on the left-hand side. The right-hand side is grounded. There's the one on the bottom is kept at some other potential. It could be a function of x, and they're spaced 4 meters apart. And this gutter extends in the z direction. So I'm gonna say, this is my y. It's the gutter. This is the z. And this is another gutter. That, and this is my x, y, and z. This must be insulated somehow, right? Because they're not kept at the same potential. So there must be some insulation in here. v equals 0 here, v equals 0 here. Okay, and find the potential inside this pipe. So region in here is what we're trying to solve. Okay. All right, so what is the general method? The method is inside the pipe, it obeys the Laplace equation, isn't it? Is this true? Inside the pipe?
Right, because we satisfy our boundary conditions.
Yeah, so this is from the Poisson. And when you don't have charge, you have Laplace equation, right? So you can see inside pipe, it does not give us any charge. It's a space. So we have the Laplace equation, and we need to solve for this general solution. And we're giving a lot of boundary conditions, right? The boundary, you have a boundary on the left-hand side, that's your wall. You have a boundary on the right-hand side, that's another wall. And you may have some other boundary conditions elsewhere. We will talk about them later. So you're giving the Laplace equation, you're giving some boundary conditions, and now we have to solve it. So first of all, we have to write out the function of x and y, right? Earlier we said this can be a function of x times y times z. Sorry, this looks too similar to my x. And sometimes we can even simplify this because not all the time, they all have dependence on all three variables. Sometimes you only have dependence on one or maybe two variables. So in this case, do you think we can simplify? So the potential inside this pipe, do you think it depends on x, y, and z, all of them? Or do you think it depends on one or maybe two of them?
I think it's going to depend on x and z.
Okay, and why would that be? Let me look at someone said the chat. Then the chat said no z dependence, but do depend on x and y. So how do we know that it doesn't have a particular dependence? So it says the metallic gutter extends in z direction. Extends meaning that it's, you can view it as an infinite large in the z direction. So if it does have a z dependence, that means, okay, I can look at the potential here along the z direction or there, it would change, right? That means it has a z dependence. Depending on your location of z, my potential changes. And because it's infinite in the z direction, do you think it could have z dependence? It would not be able to have a z dependence, right? It's extending infinity in z. So by you're looking at this metallic gutter, you still have infinite amount on the left-hand side, on the right-hand side. Physically, it hasn't changed. So because your gutter is infinite in the z direction, your function should not have a z dependence. That's something showed up before when we solved electric fields. Remember, you have an infinite sheet, then your E field doesn't depend on the x and y, right? No matter where you go in x and y, you still have that same infinite sheet. You're not closer to one edge or another, so you shouldn't have the change to E field. So that's similar, right? Similar here. So we have simplified our equation into 2D. Simply just depend on x and y can be written just a function of x times a function of y. Okay. All right. Now, the next task we need to do is let's write out all the boundary conditions we can think of. So let's stare at this picture and let's write all the boundary conditions. So boundaries is what particular location that we already know the V, right? We know three of the walls. So someone said V equals 0 when Y equals 0 and Y equals 4. Okay. So the left wall, and the right wall, right? Okay, so let's look at the left wall. This left wall is located in the YZ plane, and it is located at x equals 0. This right wall is located at x equals 4 meters, and the potential is 0. So let's try to write it out. That boundary condition for the left wall is when x equals 0, and it's showing me the above the x. Right? It doesn't really tell us anything about it. Below above the y equals 0. Nothing in below, so I'm going to be y larger than 0. The left wall is kept grounded, right? So that's my left wall. The right wall is the same thing for y, above x equals 4 meters. In this case, 4 meters. Let's just keep it a general, very general. So some distance a is 0. And there anything else? The one that's on the bottom, right, is kept at some distance v naught, some kind of function. Here v naught doesn't mean it's a constant v. It's just a known quantity. This is a known function of x. So the bottom. So how do you describe the bottom? The xz plane. Bottom wall, v something equals v naught x, which is a known quantity. So how do I describe this bottom wall? And y equals 0. Yes, very good. The bottom wall is when y is 0. And you're dealing with, okay, let me put y over here. Y equals 0. And you're dealing with a space between 0 and this region, right? We don't really know what happens at other places of the x, but within this region, the bottom wall is kept at this potential. Okay, all right. Are we done? Do you think we're done? So inside the pipe, we are just thinking about what's inside this pipe.
Would it be the top wall too, even though there's not one?
Yeah, very good. So what we can do inside this pipe? We can go left and to the right. That's changing our location in x, which will for sure change our potential. That's what we're trying to solve for. We can walk inside and outside, into the page or out of the page. That changing your location in the z. You know that doesn't do anything to your potential, right? Your potential doesn't change. We can go up and down, go up and down. We are varying our position in y. So imagine if you go up and up and up and up. It doesn't show a ceiling, right? It doesn't show a ceiling in y. But what do you think should happen when y is infinity? That you're going further away from your distribution. It has to be 0. Yes, thank you, Diego. It has to be 0. That make it a physically possible scenario. Okay, so we change in x, we change our v. We change our z, we do not change our z. We change our y, we change our z as well. Y, it doesn't have a wall. So the highest wall you can go in y is infinity, and Even though it doesn't say, we know physically it has to be like this. So any x within your what you're looking at, or actually any x, as you go to infinity, it should be 0. So we found 4 boundary conditions, and we have 4 boundary conditions that help us narrow down these constants when we are solving the differential equation. All right, so we'll keep them here for now, and we're gonna go back to use this. Remember, now when we did previously, we did, okay, now they become all become constant, so we will end up with C1 x and C2 y, right? It's just like what we did before, but now we don't have the z component. Right, this was from solving this equation, claiming C1 plus C2 equals 0. Okay, so we have 2 constants here. You have these possibilities. C1, C2 are both 0, or C1 positive, C2 negative, or C2 positive, C1 negative. Now we don't really know which one it is. We have to figure that out, because to solve this equation, we need to know, okay, is it going to be the sine cosine combination, or is it going to be e to the power of square root of C1x combination? Which format that your solution has to pick up, depending on the sign of your C1 and C2, right? So which one has to be positive? Is this correct, or is this correct? So if C1 is positive, if C1 is positive, then that tells me the function of x will pick up this particular format. Will pick up this particular format. With our particular situation, do you think that's possible? So my question is, if C1 is positive, x will look like this. Do you think this function will be able to satisfy our boundary conditions that is listed right here? I'm gonna let you stare at it for a little while. And if you have any thoughts, please let us know. Could this format satisfy these boundary conditions? Or you think about these two together, actually. If C1 is 0, then for the function of x, we have this general format, right? A plus bx. Different function, a double prime, b double prime. So do you think this could satisfy the boundary conditions? Could this satisfy the boundary conditions? We can think about a plus bx. That's a little bit simpler format. If your x is, the function of x is a plus bx, could it satisfy these two conditions?
And the reason why I say that is because if we take that second derivative, no, never mind. I take it back. It wouldn't.
It wouldn't satisfy that boundary condition you said, right?
Yeah.
Okay, yes, very good. If it were this format, it's not going to satisfy those boundary conditions. And let's see why. Okay, so the first two boundary conditions, 1, 2, 3, and 4, the first two is telling me v at x equals 0 is 0, v at x equals a is 0. Okay, let's say this is, and your v is a function of x, y is a function of x times y, okay? So this means as your x changes, your v is going to be 0. So which means as your x changes, what is changing your value is not going to be what happened in y. It's only going to be what happened with your x function, right? So when you say, okay, x equals 0, this is 0, that means a plus 0 is 0, a is 0. So that becomes v sub x, right? Now, could that also satisfy the condition of x equals a is 0? I plug it in, you get b times a. Well, it's not 0. There's no way for that to happen. Then the only way for that to happen is b is also 0, then you get a trivial situation. So that wouldn't work. This one is no good. No good. So now looking at this one, could this one work? Could this format work though?
Yeah, it could work.
Okay, let's see. This one, okay, let me plug it in again. At x equals 0 is 0, tell me e to 0 is 1, right? So a plus b is 0. Means a is equal to negative b. Okay, all right, so that means this becomes a e to the power of this minus, sorry, we don't have a b because I changed that to a, e negative c1x. Right, this function become like this, and it also needs to satisfy at a. Could it also satisfy x equals a, x equals a, this becomes a e c1a minus e negative c1a. Is this 0? It's not 0, right? These two are not the same number. One minus the other is not going to be 0. It might satisfy one of the boundary conditions. It's not going to satisfy both. So this one is no good. Doesn't work. Okay, so by sort of eyeballing this, we figured out the only solution is when C1 is less than 0. So they have to pick up this format. So it seems like C1 has to be less than 0 and x has to be in this particular format, a sine of negative c1x plus b cosine of negative c1x. Now negative c1 is not easy to calculate, so it's not easy to write. So I'm going to say, I'm saying k squared is going to equal to negative c1. Okay, so a lot of times we write k instead of negative c1. That's just annoying to write. So it's going to be just kx plus b cosine of kx. Okay, sine kx. So b kx. Okay, all right. So that's our x. So if I found x, what can you conclude about y? C1 plus C2 is 0. So I said C1 is negative. So C2 is negative C1, which is positive, right? Which is K squared. So C1, so K squared is C1, and that's equal to C2. Okay, so will you be able to tell me what this function of y will look like? So C2 is positive. Your C2 function is going to look like this, right? C1 looks like this. C2 looks like this. So y function looks like, okay, I'm going to write it out. It's going to be some constant times e to the power of root C2 x plus some function to the power of negative C2 x. C2 is k, right? C2 is k squared. So c e to the kx plus d e to the negative ky. I'm sorry, this is y, because we're dealing with the function in the y direction. C2y, C2y, ky, ky. So I've got those two equations. This is one of them. This is another one. Okay. Managed to find the specific format of how x should change with respect to x and how y should change with respect to y. And they should look like this. Okay, I'm gonna pause for a little bit and ask, at this point, are there any questions before we move on? With the process that we went through to narrow down, I think the difficulty would be to figure out which one has to be the positive variable, which one should be negative. Which one is positive constant, which one is negative constant. So, or the boundary conditions. Are there any questions right now? So please ask your questions before we continue further.
Professor, I have a question.
Yes, go ahead.
So I think I kind of agree with what you said. I think the difficulty lies within like if C1 or C2 is positive or negative.
Right.
And so to determine that is we look at the boundary conditions.
Mhm.
Okay.
We look at the boundary conditions. The boundary condition said, oh, at x equals 0, it's 0, at x equals a is 0. With this particular format of the function, could it possibly behave that way, right? Sometimes it's not exactly like this, but it could be, my boundary condition show me that the function of x has to be an even function. But if it looks like this, it's not going to be an even function. Or my boundary condition says my function in y has to be an odd function, but this format doesn't work. So it's by looking at your boundary conditions to narrow it down. So, okay, right, if you feel comfortable now, let's try to solve a question, answer a question together. Then this will look a little bit more concrete without, it's hard to think about this without a concrete example. I'm gonna give you another sort of situation. You have these two differential equations, right? C1, C2, and this is your boundary conditions. Okay, given this particular boundary conditions, which one of these has to be assigned to the negative constants? Okay, so take a screenshot of this before you go ahead and discuss within your group. Here is our question. Okay, another 10 more seconds. So put in your vote. Okay, all right, let's take a look at this together. I'm gonna go ahead and close it. This is our result, right? C seems to be the most popular where both of them zero. If both of them zero, they're gonna be just a linear function of x and y. Okay, all right, and then B is the next popular, and then followed by A and C. And then B. Okay, so let's look at the behavior of these boundary conditions. What we emphasized earlier is, earlier we had x equals 0, b is 0, bx equals a, it is 0. That's, what does that tell us? That tells us it cannot be which format? It cannot be a e to the power x plus b e to the power x format, right? We said this is no good, remember? We also said this is no good. This wouldn't work, this wouldn't work. So now we have a new situation. So what do you think? What do you guys think? What is now zeros are the one that changes with y. So this boundaries, you can translate it into equation. This is telling me v at y equals 0 is 0 potential. V at y equals some kind of number, let's say it's b, is 0, right? That's how you translated this into equations. So what does that tell us about the specific format for the y solution? Anybody?
That it has to have a negative c.
Yeah, it has to have a negative c for the constant associated with the y. That constant needs to be negative. Yes, which means the y must be the sinusoidal kind of function. So it has to be like this. And C2 is the negative one. Okay. You can always verify saying, well, what if there's this? Well, you can do this. If it is a plus by, if C2 is 0, tells me it is this format. And you plug in y equals 0 is 0. And you can see that it cannot satisfy them at the same time. If this is satisfied, this is not. Okay. So C2 is 0 won't work. If C2 is larger than 0, will not work either. It's just the same process we went through. So, okay, so figure out y. This is y, right? Then the other side must be the x, must be the C1 is positive. So x will actually have the e to the power of x plus e to the power of negative x format. So that's what we do. Okay, so even more, you probably noticed some of these functions, if I switch my y to be sort of in the middle, if I shift everything boundary condition to be in the middle, then you notice that your function in x is, okay, at x equals negative a is the same value at x equals positive a, right? Showing you the function of x has to be even, needs to be an even function. You can even narrowing down for sines and cosines. If it were sines and cosines, you can narrow it down to be exactly which one, or sinc or cos. You can even further narrow it down. We will have more examples to figure that out later. But this one, all you need to look at is the 0 ones, and the other one is pretty much figured out if you have one of them figured out. Okay, so this is a little detour we took. Followed by next week, we're going to continue to solve this equation. We're not done with this yet, right? We got these general solutions, but we haven't found these constants. We're going to continue to do that next week. All right, I'll see you guys. If not at office hours, I'll see you in our recitation. And you're welcome to come to office hours if you're preparing for your exam for next week. Encouraged to come and ask questions. Okay. All right. See
Thank you, Dr. Ryan.
Bye.
Thank you, Dr. Ryan.
Thanks, Dr. Ryan.
Thank you, Dr. Ryan.
Thank you. Bye, everyone. No, Benjamin, there will not be a review session. Well, oh, you mean in class? Let me see. Give me 1 second, Benjamin. The recitation this week will be sort of like a review. We'll solve some problems that is going to be related to the topic that's going to be on the exam.
I have a small question just about the just one of the conditions. When you did the linear one where C1 equals 0, why couldn't B be 0 and then make that condition?
If that's the case, you will get 0 potential everywhere within, and it will violate the boundary condition on these two sides.
Oh,
Yeah, because
okay.
if you make B is 0, that means for every Y, you got 0. So that means not only just this wall and this wall, so everywhere here, whatever Y is 0, right? And
Yeah.
that's not
Okay. Okay, that makes sense.
okay. Thank you.
All right, thank you.